Okay, so first, of course, let me thank the organizers. It's a great pleasure to be here. So I'm going to be, on this talk, I'm going to try and be a little bit light on the math and heavy on the drawings. So please, if something is not clear, feel free to interrupt me. So I'm going to talk to you about some joint work with Brune Massoulié that's very much ongoing and will be carried on with Christina Toninelli as well in the future. So just so that everyone is on the same page, I'm going to start with a very basic model that I guess most of you are already familiar with, which is the SSEP, so the symmetric simple exclusion process. So I'm going to consider the SSEP on the ring. So my ring has k sites. And each site, of course, is either occupied by a particle, in which case the configuration variable is 1, or empty, in which case the configuration variable is 0. Okay, so a configuration is going to be a collection sigma of zeros and ones, zeros for empty sites, ones for particles. Now, given a starting configuration, your particles start to jump, and in the SSEP, particles jump at rate 1 to any vacant neighbor. So, for example, this particle cannot jump right, and this particle cannot jump left, but otherwise, all of the jumps occur at rate 1. Okay, so this is a very well-known and well-studied model. And in this talk, in the first part at least, I'm going to consider a variant of this model, which is the SSEP with traps. So in this variant, you still have the option for any site to be occupied or empty. So I'm still on the ring of size k. And each site is still either occupied or empty, but you have a third case, which is possible, which is that the site contains a trap. Okay, and this trap is characterized by depth. So A here is a negative number. So absolute value of A is a positive number, of course, and it's going to be the depth of the trap. So here you have a trap of depth 2. Here you have a trap of depth 1. Here you have a regular SSEP empty site. And here you have an occupied site. Okay, so this is very similar to the SSEP, except that you have these traps here and there with no specific assumption on where they are for now. Okay, so this defines a configuration for your particle system. Now, of course, I need to talk about the dynamics. So the dynamics is going to be very much like the SSEP, which means that particles are going to jump to at rate 1 to any neighboring site, provided that the target site is not occupied. Okay, so for example, this jump is not allowed. Particles can jump to empty sites just like in the SSEP. And now I have to define what happens when a particle jumps on a trap. Well, as you may expect from my drawings, when a particle jumps through a trap, the particle is going to be, so it falls down the trap, the particle is destroyed, and the trap loses 1 depth. And if the trap was only depth 1, well, the particle falls, it is destroyed, and now the trap has completely disappeared. Okay, so it's not exactly conservative in the sense that particle can get destroyed, but it is conservative in the sense that every time a particle gets destroyed, the system loses 1 trap depth. Okay, is the model clear? Yeah?
Excellent. A quick question. So,
yeah.
Is there any bound for the depth? I mean,
so the depths can be pretty much anything. So it depends from what perspective you're looking at, but if you take a fixed k, okay, since you have at most k particles, pretty much any trap with depth larger than k does not matter. It's just going to be, for all purposes, it's going to be an infinite trap. Okay, but I'm going to come back later to that point. Any other questions? Okay, so you have your SSEP with traps, and here, of course, you can write the Markov generator. I'm not going to use it very much, but just so, once again, just so everyone is on the same page. So your generator for your process is that a particle jumps from k to k plus z, where k plus z is one of the neighbors of k, provided that you have a particle at site k, you have no particle at site k plus z, which means either you have an empty site or a trap, and then the particle jumps from k to k plus z by removing the particle at site k and adding 1 unit to site k plus z. So when we essentially discovered somehow these dynamics, I will explain later on why we came across this model. This dynamic is actually very close to an article, to the model considered in an article by Funaki, which was interested in completely different questions. So Funaki's article essentially was a SEP with traps, except that the trap depth was constant, more or less. And Funaki was interested in the macroscopic behavior of the system and proved that you had, at the hydrodynamic limit, you had a Stefan problem where the particle essentially invaded the traps. Okay, so a few comments or a few properties of this model. The first one is that the depth of any trap can only decrease. Okay, this is straightforward because the only way for the trap depth change, the only way for the trap depth to change is if the particle jumps in. Okay, in the same way, the total number of particles can only decrease because particles are conserved except if they fall into a trap. The second remark, which is very important, is that the SEP with trap dynamics is attractive in the sense that Christina was talking about earlier today. And maybe it's worthwhile for me to spend a little bit of time to explain what that means. So it's attractive in the sense that if you take two SEP with traps, okay, so for example, this one with one trap here and two particles here, and this one with a trap of size 2 here and just one particle here. Okay, so clearly you see that this one is larger side per side than this one. Okay, so psi and psi prime. Well, the system is attractive in the sense that there is a way to couple the evolution of those two steps with traps in such a way that if initially you have this monotonicity, then at any time t, psi of t is still going to be larger than psi prime of t. And the way to build this coupling is actually very straightforward. You can imagine that you have a clock associated with each edge in your system. Well, when you just put the same clock on the same edges in both systems. Okay, so if this particle jumps, if this clock rings, for example, well, here you have the exclusion rule, so those two particles are not going to move, but this one is going to jump here. Okay, and you see that after the jump, this one is still larger than this one. Okay, in the same way, if now this edge rings, I don't remember where my particle was, but imagine it's here. Well, here nothing happens. Here the particle jumps into a trap and deletes the trap, and your monotonicity is preserved. Okay, so you had this very nice coupling that ensures, in some sense, that monotonicity is preserved by the dynamics. So if you have some control at the initial time, then you will also have some control at any later time. Another remark, which is very straightforward as well, is that when the last particle gets trapped, well, the SEP with trap is completely frozen. Okay, you only have remaining traps. You have no longer any particle, so nothing happens in the system. And the other way around, when the last trap gets filled, you only have particles, and then you're left with a classical SEP. Okay, this is exactly the SEP dynamics. Okay, but until one of those two things occur, so either the system freezes or it becomes a SEP, you're left in a transient state. Meaning that at some point, either the last trap is going to disappear, or either the last particle is going to disappear. But you cannot have forever coexistence of traps and particles. Okay, so you're left in a transient state until one of those two disappear, and I'm going to call TK my set of transient states where both traps and particles coexist. Okay, so the question I'm going to be interested in is how long does it take, how long does the system stay transient in the worst case scenario? Okay, you can take any configuration you want for the SEP with traps. How long is it going to take to stop being transient? So either to freeze or to become a SEP. So I'm going to define the transience probability. So pk of t is the worst probability to still be transient at time t. Okay, so you start from any initial configuration, you take the worst one, so you take the supremum, and you take the probability starting from psi that at time t you are still transient. Okay, and I'm going to define the associated transience time, which is theta k of epsilon, which is roughly the inverse function of pk of t. Okay, so after time theta k of epsilon, you know that the probability to still be transient is going to be of order epsilon. So the first result that we obtained with Brune, which is fairly straightforward, is not the hardest one, is that the transience probability, so this quantity here, vanishes uniformly over time scales of order k squared log k. What that means is that if you take the transience probability at time tk squared log k and you let t go to infinity, then this goes to 0. Okay, so this gives a first indication that probably the transience time is of order k squared log k. So this is a rather crude estimate. It's crude in the sense that I'm not saying much about the behavior of the transience probability. Okay, I'm just saying that over those timescales, provided that you let the t diverge, you're going to reach 0 for your transience probability. So before going to the second result, which is a little bit harder, let me talk about attractiveness and critical transience. So I'm interested in the worst case scenario. Okay, I'm interested in the worst case scenario from the transience time. So a very natural question, if you're trying to understand the worst transience probability, is to try to identify the configuration that's going to yield the worst result. Well, we cannot really do that, but we can narrow down a little bit the scope of our research. And the way to do that is with attractiveness, this property here that I was mentioning, which gives way to a lot of coupling arguments. So let me call S, so S of psi is what we call the number of excess particles. So if S of psi is positive, this means that in the system there are more particles than trap depth. If S of psi is negative, then it means that there are more traps than particles. Okay, so this is S of psi. So S of psi equals 0, we'll call that a critical configuration, which has exactly as many particles as trap depth. So when a critical configuration is no longer transient, it's just 0. Well, with attractiveness, you can see that if you have a supercritical configuration, so with more particles than trap depth, well, it's going to take a shorter time for this one to become a SSEP than for this one. Okay, because here I have increased the number of traps. So if this one is no longer transient, then for sure you can couple the evolution with this one in a way such that this one is no longer transient either. Okay, so the critical configuration, at least in the supercritical case, is going to be with the worst. Is going to be among the worst case scenarios.
Did you fix the total size of the traps?
Well, I mean, no. It can be changed the way you want. But what I'm saying here is that actually,
well, I can put infinite traps everywhere.
Yeah, of course. But then the transience time is very short.
So the result must depend on the size of the trap.
Well, yeah, because I'm taking the worst case scenario.
But worst case scenario, I can put anything.
Yeah. But so the transience time for a configuration with a lot of traps is going to be very fast. So it's not going to be the worst case scenario. You're going to remain transient a very low amount of time, a very short time. Because your particles almost immediately are going to jump over the traps and get deleted. Okay? I'm interested in the configurations that are going to yield the longest transience time. And for those, attractiveness tells you that you need to check for critical configuration that have exactly as many particles as trap depth. Is it clear?
This does not depend on the number of...
Well, I mean, between a configuration, among critical configuration, it's not so clear which one are the worst. But in any case, if you want to define a critical configuration, you have at most k-1 particles, because you have k-1 occupied sites, and then k-1 trap depth over one site. Okay, and for subcritical configurations, well, essentially the reasoning is exactly the same, and you can convince yourself that a configuration with a lot of traps is going to become frozen faster than a critical configuration because you're just adding up particles, so you're making it harder to become stuck. Okay, so now we have completely removed supercritical and subcritical configurations for the equation. If we want to understand the maximal transience time, we're just going to look at the critical configuration. Okay, so now for a moment, let's assume, let's forget that our particles interact via the exclusion constraint. Okay, and let's assume that our particles jump just completely independently. Okay, so now you no longer have a cap on the number of particles per site, of course. And let me try and let me try and give you a sense of these tk square log k. It's actually a very short heuristics. If you take a single particle and you put a trap on the other side of the system, well, the time it's going to take for it to discover the trap, in some sense, is going to be upper and lower bounded for. So the probability that the particle has discovered the trap before time t is going to be, has not discovered the trap before time t, is going to be upper and lower bounded by quantities like that. 1 minus e to the minus ct k square. Okay, and this k square here means that the particle comes from the fact that the particles are going through a diffusive motion. Okay, so you have a probability qk of t of remaining free, that the particle has not fallen into a trap before time t. Now, if you're looking at k independent particles, it's a very easy computation, and you work a little bit on this quantity, and you get this quantity here for the probability. At least you get a bound. Okay, and now you see that if t is k square log k times a constant, and this constant goes to infinity, then this is probably the right order for pk of t. For the lower bound, well, then you can just consider a very specific configuration, and the specific configuration you can take is just k particles on one side and a trap of depth k on the other side of the system. Then, once again, it's a very easy computation, and you get exactly the same kind of bound, which tells you that k square log k is really the right time frame. Okay, so this is a very crude bound because I have considered only independent particles, but essentially this gives you an idea of where this quantity comes from. Okay, so now a harder result is, can we characterize the part of the curve where I had my question mark? And actually you can, and what we prove is that the transience time actually exhibits a cutoff at a very specific time. And this specific time is this tk star here, which is k square log k times pi square. No, 1 over pi square, sorry. Okay, so what does this mean is that the probability, the worst probability that the Sep-Witz trap is still transient at time t goes through a very sharp transition where it's going to be 1, 1, 1, 1, 1 up to a time which is essentially k square log k divided by p square. And then during a very short time window, and by very short I mean smaller than k square log k, it's going to drop down to 0, and then of course stay to 0. So cutoff is probably a terminology that most of you are very familiar with, and usually you talk about cutoff for the mixing time, and here it's one of the rare instances that we've found where cutoff can be applied to something else than the mixing time. Are there any questions on? Oh, sorry. Are there any questions on this result? No. Okay. So now that we have cutoff for the transience time, a natural question is what happens for the mixing time for the Sep-Witz traps? Well, for the Sep-Witz traps, if you fix the number of excess particles, so the number of excess particles is the number of remaining particles once you have spent your transience time. Okay? So the stationary state for the Sep-Witz traps, provided that the number of excess particles is S, is just uniform over Sep configurations. So here the state space is 0, 1 to the k, with S particles. Okay, and in the same way that I define the transience probability, the transience time, you can define the mixing time, which is just the smallest t, the smallest time, such that the total variation distance between the distribution at time t and the stationary state is less than epsilon. And what happens is very interesting, is that, so I mentioned that the worst case scenario for the transience time is the critical case. So the critical case is this one here, where the number of excess particles is O of 1. See, it's actually, in the critical case, S is just 0. So in the critical case, you have a large transience time, but once this transience time has passed, your configuration is empty. So the resulting Sep mixes instantly. So it's not very interesting from the mixing time perspective, but it's interesting from the transience time perspective. Now you can take a configuration where the number of excess particles is of order k. So for example, so you have a system of size k. you can take, for example, k over 2 plus delta k sites, which are all occupied. And then here, you put a trap of depth k over 2. Then your excess number of particles is going to be delta k. And you can ask yourself, what is the transience time and the mixing time going to look like for this kind of configuration where I have a macroscopic amount of extra particles. And as it happens, in this case, well, the transience time is much faster. It's much faster because you have much more choices regarding the particles that are ultimately going to fall into the trap. So you're introducing some entropy here. So the transience time is now going to be of order k square, so it's going to be diffusive. But the mixing time is going to be now of order k square log s, but s is of order k. So now the mixing time is long, k square log k, but the transience time is going to be short. Okay, so you have kind of this balancing out between transience time and mixing time, which we found kind of interesting. Okay, and the mixing time for the SSEP is very well known, and in this case, the result we use come from an article by Hubert Lacroix in 2017. Okay, so this is what I wanted to tell you so far about the SSEP with traps, and now I want to talk a little bit about how we got to this model and why we found it interesting. And the reason is another process which is called the facilitated exclusion process, which bears some similarities with the facilitated processes that Christina talked about earlier, except that, so this is the facilitated exclusion process is still a one-dimensional process, still on the ring, but the ring, for reasons that will be clear later on, hopefully, is going to be of size n rather than k. Okay, and this is an exclusion process, which means that particles can only jump to empty sites, except that you put an extra constraint on the motion of particles, meaning that a particle can only jump to an empty site if its other neighbor is occupied. This means that this particle, which has no occupied neighbors, cannot jump. Okay, so this is a kinetically constrained model, but in a very different sense than what Christina was talking about, because she was talking about Glauber dynamics, where particles get created and deleted. And this is a Kawasaki dynamics, which is conservative, where particles move around in the process, provided that some constraint is locally satisfied. Okay, so we have this system where particles can only jump if they have an occupied neighbor. Once again, a few remarks. First, if all particles like this one are surrounded by empty sites, well, the system is frozen. Okay, no particle can jump because of the constraint. A second remark is that if empty sites are isolated, then we are in what we call an ergodic state. What I mean by that is that if you take a look at what happens in the system, well, if you have a pair of neighboring empty sites, you're going to be able to break it down in the sense that a particle can jump in, and now the two empty sites are no longer neighbors. Okay, this can happen. The reverse, however, is not possible, meaning that two empty sites cannot become neighbors. Why? Because in order for those two empty sites to become neighbors, the empty site needs to jump here, which means that the particle needs to jump there, but it cannot because of the exclusion constraint, the kinetic constraint, sorry. Okay, so this means that once all your neighboring empty sites are separated, they cannot become neighbors again, which means that once you get to an ergodic state, you remain in an ergodic state. Once again, like for the SSEP with traps, until you get either frozen or ergodic, you're in transient state where you have both active particles, meaning pairs of neighboring particles, and pairs of neighboring empty sites. Is the definition of the SSEP clear? Yes? No? Yeah? Okay. Okay, so since you have also this transient regime, you can ask yourself exactly the same thing, which is how long, I didn't even change the SSEP with traps here, but now this is for the FEP. How long does the FEP stay transient starting from the worst configuration? Okay, so you define exactly the same thing. You define the worst transient probability, which this time depends on the size n of the system. You can define the transience time as well. And you obtain a very similar result, except that the cutoff time is no longer t star k, it's t star n over 2. Okay, but it's exactly the same expression in some sense. And the correction here is exactly the same as well. Okay, so of course, if I'm mentioning the SSEP with straps and then I tell you about the FEP and I mention two results that look eerily the same, there must be a connection between the two. And the connection is this one. You have a very nice mapping between the SSEP with straps and the FEP. So you start from a FEP configuration, okay, and you're going to number its particles. And these particles in the FEP are going to correspond to sites in the SSEP with straps. When you look at a particle in the FEP, you look if there is a particle next to it. If it is the case, then you put a particle on the corresponding site in the SSEP with straps. If there is a particle followed by an empty site followed by another particle, then you put an empty site. Okay, so particle, empty site, particle, empty site, empty site. If there is a particle followed by a larger number of empty sites, then you're going to pile down your empty sites and create a trap in the SSEP with straps. Okay, so here you have your normal empty site, and then you have two extra empty sites, which means that you're going to have a trap of depth 2 in the corresponding site 4. Okay, once again, here you have a particle that's followed by a particle, so this is a particle in the SSEP with straps. Particle followed by two empty sites, so this is a trap of depth 1. Particle followed by a particle, this is a particle. And particle followed by, okay, hopefully one single empty site, this is an empty site. Is this mapping clear? Yeah? Okay, no, so now of course you can ask yourself dynamically what happens, and you already know what happens because I defined already the two processes. If you take a look in the FEP at what happens when a particle jumps, so for example the particle that was here wants to jump here, well, you're going to increase the space after this one by 1, and you're going to decrease the space after this one by 1. So essentially what happens is your particle that was here is going to jump here. Okay, so this is exactly a SSEP-like behavior. Now, if this particle jumps here, well, this amount of empty sites is going to decrease by 1, but the following number of empty sites is going to increase by 1, which means that the particle has fallen into a trap. Okay, so you have this one-to-one mapping between both static and dynamic features of the FEP and the SSEP with straps. And now you can take a look at what happens for a critical FEP. So a critical FEP is one with exactly half the sites occupied. Well, this critical FEP, you're going to be able to map it to a critical SSEP with straps. Okay. So for example, maybe let me represent it this way, for example. So you have, okay, of course I chose an odd number. So maybe let us look at this one. So you start your mapping, for example, from this site. So you have 3 particles, so your SSEP with straps is going to have 3 sites. Okay, so this is a critical FEP, because in its stationary state, it's just going to be an alternated configuration. It's going to be particle, empty site, particle, empty site, particle, empty site. And once you map it, well, this one is going to be this one. So here, the particle is followed by a particle, so I have a particle here. This particle is followed by a single empty site, so it's just going to be an empty site. This particle is followed by 2 empty sites, so it's going to be a trap. So here you have a trap. Okay, and you see that a critical configuration maps into a critical configuration. And since you have this trajectory per trajectory mapping between configurations, since you have this correspondence between trajectories, you know that the time you become ergodic or frozen for one process is exactly going to be the time you become ergodic or frozen for the other process. So you know that the supremum of a critical configuration of the transience time for the FEP is going to be exactly the supremum of a critical configuration to be transient for the SSEP with straps. And this one, we already know thanks to attractiveness. I mean, not thanks to attractiveness, but we already know because of the previous result. Okay, this is just T star n over 2. Okay, so because of this mapping, you already know the time needed for the facilitated execution process, at least the critical one, to become transient, to stop being transient, and it's going to be T star n over 2. The problem is that for the FEP, we don't have attractiveness. So this means that for the FEP, we don't know for sure that the worst case scenario is going to be the critical one. So you need to find a little bit of another argument. But since we have a lot of information about the SSEP with straps, we can cheat a little bit. So now consider a subcritical configuration for the FEP. Okay, so this configuration has less than half of its sites occupied. Well, you can map it to a SSEP with traps, psi eta, using the previous mapping. And you know that the transience time for eta is going to be the transience time for psi. Okay, this is because of the mapping between trajectories. But you know that psi is subcritical as well. So its transience time is going to be lower than a critical configuration for the SSEP with trap that you can associate it with. So here I have an illustration of this. You start from a FEP configuration. You map it to a SSEP with traps, which is subcritical as well. Well, the transience time for this one is going to be smaller than the transience time for this critical configuration here. But the transience time for a critical configuration, we know, is tk star, where k is the number of particles in the initial FEP. And since k is less than n over 2, tk star is less than tn over 2 star. Okay, so now the subcritical case is solved, because you have proved that the transience time for your subcritical FEP is less than tn over 2 star. And you know that for critical configuration, it's tn over 2 star. So now you only have to deal with supercritical configurations. Well, so what I essentially explained here is that subcritical configurations for the FEP, we know freeze faster in some sense than critical ones. Well, you want to do exactly the same thing for the supercritical configuration, meaning for FEP configuration with more than half the sites occupied. The only trick is, so this identity still holds, because it does not depend on the number of particles. This identity still holds, because a supercritical SSEP with traps is indeed faster than a critical one. But this time k is larger than n over 2, so this last bound here is not good. So we need to find another way around it. And actually, the other way around this is just using another mapping that essentially uses the opposite. Instead of building sites on particles, you build sites on empty sites. I think I'm not going to get too much into it. Oh, yeah, I have a little bit of time still. OK, so to treat the supercritical case, we use another mapping. So here you still have a FEP configuration. And to go to the mapped configuration, instead of piling down traps, you're going to pile up particles. So now your sites in the mapped process are going to be determined by the empty sites in your configuration. And you're going to pile up the same number of particles following the empty site. Okay, so this is a very classical mapping. This is a mapping between exclusion configuration and zero range configuration. It's been widely used for a number of applications. And dynamically speaking, if this process is ruled by the facilitated exclusion process, then this process is fairly simple as well. Each site is going to make a particle jump at rate 1 if the particle is not alone on its site. So here, one of those particles would jump at rate 1 left and at rate 1 right. However, this particle here would not be able to jump and would be stuck until another particle comes along. Okay, so this is a rate 1 zero range process, which is also constrained, and importantly, which is also attractive. And now we can use essentially the same reasoning as in the previous slide. So let me call omega the configuration for this zero range process. The transience time for my supercritical FEP is going to be exactly the transience time for my zero range process. Because the zero range process is attractive, this transience time for the supercritical case is going to be smaller than the transience time for a corresponding critical configuration. You can map it back to the SSEP with traps, but this time with a critical configuration that has n minus k sites rather than k. And now n minus k was larger than n over 2. So n minus k is smaller than n over 2. And you're left exactly with the bound you wanted. OK. So this tells you that indeed, even for the FEP, the worst case scenario is indeed the critical one, which was kind of intuitive, but because we lacked attractiveness, was not so easily demonstrated. But with two kind of clever mappings, you can actually get the result you want. Okay. So now, of course, I've talked about the transient time for the SSEP with traps. I've talked about the mixing time for the SSEP with traps. I've talked about the transient time for the FEP. Remains the mixing time for the FEP, which is a very natural question. Unfortunately, transience time goes immediately from SSEP with traps to FEP. This is straightforward. But this is not the case for the mixing time. And the reason is this mapping here is defined up to the position of a tagged particle. And because the mapping is defined up to the position of a tagged particle, you need to know where the tagged particle is at any time to be able to have a one-to-one correspondence between dynamics. So imagine that your SSEP with trap has fully thermalized, meaning that it's exactly in its stationary state. This does not necessarily mean, or at least it's not straightforward to prove it, that the mapped back FEP is also in its stationary state, because you have some unknown on the position of the tagged particle. Okay, so this is ongoing work. We're trying to solve this problem, but it's not completely straightforward to understand the mixing time. You need to understand the joint distribution of the tagged particle and the configuration, which is a little bit tricky. Okay, to conclude, just a couple of minutes on the proof. So once again, since by attractiveness, I have completely removed from the equation the supercritical and subcritical configuration, so I only need to understand very finely, very specifically, the critical configurations. Okay, so let me take a look at critical configurations. And the first natural question is what happens if you have a single trap? Okay, so you take a critical configuration with a single trap. Well, I mean, since in any case, if you just look at the particles here, you can treat the single trap as an empty reservoir. Okay, because once all the particles have been removed, and they are being removed at rate 1 as if this site was a reservoir, well, essentially once everything has disappeared, nothing more happens, so the bulk of your system is going to behave exactly like a SSEP in contact with reservoirs. So the transience time for this configuration with a single trap is exactly is related to the boundary-driven SSEP mixing time. Why? Because essentially what I was mentioning is that, so recall that we are in a periodic setting, so this trap here is also connected to the other boundary. So what happens is you're putting your 4 particles here at both extremities in contact with a reservoir that removes the particles at rate 1. But the mixing time for the boundary-driven SSEP is very well known. So the transience time for the case of a single trap is well known as well. Okay, so fair enough. This is fairly straightforward. And also another remark is that by attractiveness, if you have a single trap but with less particle, so this process is going to take less time to stop being transient than this process. This is just an attractiveness result. Okay, so the worst case scenario is this one, and this one you know exactly how to treat it because you know very well the mixing time for the boundary-driven SSEP. So now you need to take a look at the general case where you don't exactly know where the remaining traps are, and this is of course where the bulk of the difficulty is. The gist of it is you're going to break your system into pieces, and these pieces are going to you're going to break your system into log k pieces. And actually, this log k is exactly where is my main result? Yeah, this log k is exactly the amount we are losing here. So you break your system into pieces, into log k pieces. And you know that if you are still transient at time t, well, one of those pieces, so recall that you are in a critical case. So if you are no longer transient, then your system is just empty. If you're still transient at time t, this means that one of your pieces still has a trap. Okay? So essentially what we are left estimating is this probability here, the worst transience probability, which is less than q by just union bound, times the probability starting from the worst configuration xi, that xi of t still has a trap in one of the pieces. Okay, the problem we're looking at is complete translation invariant, so here I can take any of the AIs. I have my set A1, and I know that at time t, somewhere in A1, there is still a trap. And of course, somewhere else, there are still maybe a couple of particles, so probably something like that. Maybe there are traps elsewhere, but we don't really care about those. Okay, so the point is, and what makes the whole proof work, is that because you know that there is still a trap in A1, this completely breaks, or this somewhat breaks the periodicity of the system. Because you know that no particle can have fully crossed this set A1. Otherwise, it would have fallen in the remaining trap. And since it breaks the periodicity, well, we can kind of copy our system in such a way that particles roughly have the same motion in the periodic setting and in the segment setting, in such a way that here, so maybe let me call B1 the bulk. Okay, so B1 is the full torus except A1. So here you're going to copy B1, you're going to copy A1, and instead here of putting periodic boundary conditions, you're going to create a copy A1 tilde of your set A1. And essentially you're going to work to couple the dynamics on this circle, the dynamics on this set, that you put in contact with empty reservoirs at both extremities, in such a way that if there is still a trap in A1, the particles here and the particles here have exactly the same motion. Okay? So there is a way to do that. It's a little bit involved, but there is a way to do that. And this way, you know that if this is still transient, then this means that there are still particles here. Okay? And if there are still particles here, this is roughly a SSEP in contact with reservoirs. Okay, it's a little bit larger because here you have site 1, here you have site k, and here you have a copy of a set which is of size k over log k. Okay, so you lose a little bit of information, but essentially you do exactly that. And this way, now you're left with the exact same problem that you had before about the mixing time for the SSEP in contact with reservoirs. The most tricky part is that since here you are in a periodic setting, it could happen that two particles jump here and here, because you need to distinguish your particles, essentially, which would result, because you have copied your set, in a particle jumping here and the same particle jumping here. But these are simultaneous jump, and simultaneous jump cannot occur for the standard SSEP in contact with reservoirs. Each particle is supposed to have independent clocks. Okay, so you have a number of technical issues to deal with. You need to be very careful in the way you define your Poisson clocks on this coupled process, but it can be done. And because you have lost your k over log k in the size of the system, you lose a little bit in your estimating of the transience time, but you don't lose enough so that you lose track of the cutoff. So because of this technique, we are able to actually prove that there is cutoff for the transience time. Okay, so let me maybe stop here. A couple of comments and open problems on this question. So first, we came across the SSEP with trap because we were trying to understand the FEP. But we feel like the SSEP with trap is a very interesting model in its own right. It's very easily defined in other settings, on other graphs, on higher dimensions, for example. And the results we obtain are a huge improvement with respect to what we were able to do before, because until now, we mostly used this mapping with the zero-range process. But with the zero-range process, since particles jump at a rate 1 regardless of the number, one particle jumps at rate 1 regardless of the number of particles per site. If you have a lot of particles per site, essentially your particles are moving kind of slow. So if you want to get sharp bounds on, for example, a transience time, it's very tricky to get them from the zero-range process because you lose some information on the jump rate. And as I mentioned, this proves that you can disprove a cutoff phenomenon in a new setting than a mixing time. So as I mentioned, the question we're interested in now is a mixing time for the FEP. So this is kind of tricky for the reason I mentioned. Another question which is very interesting and should be quite natural is to try and identify the worst critical configuration for the SSEP with traps. And we expect that the worst one is fully occupied with a single trap of depth k minus 1. But so far, we have not been able to prove it. Okay? And okay, it could be that actually the worst one is k over 2 and k over 2. But this, Brune has made a few simulations that tell us that probably the worst case scenario is a single trap one. And we're trying to understand how to prove that. Okay, and when we're done, maybe we can take a look at the transience and mixing time for the boundary-driven FEP. But this is tricky as well because those mapping arguments become very delicate once you put boundary interactions, because you can change the size of the map system. Well, thank you very much, and don't forget to check out Brune's poster if you want to learn more about this.
Thank you very much for the interesting talk. So are there any questions or comments?
Maybe I may ask I have a very naive question. So okay, you talk about this SSEP, but for example, if you think about ASEP like asymmetric extrusion,
yeah.
So do you expect a similar time scaling or drastically changing?
So the k square log k, the k square part comes from the fact that you have asymmetric jumps. Okay, because it's a diffusive time, and the log k is the price you pay because you need k particles to have essentially the same behavior. So of course, for ASEP, for example, or ASEP with traps, the time scale would change. And I'm not sure about that, but I think the log k would maybe be lost because ASEP has a much less random motion than SEP. I would need to check that, but it costs much more for ASEP to perform a deviation in the way it moves than for SEP. So I would expect that maybe you lose also the log k and it just becomes k.
Are there any other questions, comments?
Just you mentioned generalization in higher dimension, but you expect it will be more or less the same phenomenon, like just one trap very hard to find?
Well, in 2 dimensions, I don't really have an intuition of what happens. Essentially, what happens here is that you need to get a heuristic notion of what happens, you just need to understand how long it takes for a particle to discover the whole system. Roughly, that's that. And so I guess in 2 dimensions, you just need to take a look at the time for a single random walk to explore ZD. So I would expect the behavior to be the same, but I'm not sure.
Any other questions, comments? If not, let's thank Clément again.